Predict the next exam date. Good question. I'd say roughly 2 weeks. Okay. You will definitely have at least 1 week, 1 week's notice. So let's say about 2 weeks. Okay. Okay. All right. So let's go over the exam. Okay, so the first 10 questions were multiple choice. So let's start by going over those. Okay. All right, so the first question was which of the following is not a proposition, which is not a proposition, all right? All right, and you were given 4 choices. A was the statement water is wet. That is a proposition, right? It's a declarative statement. B was the statement x is less than 7. Okay, so that one is the one that's not a proposition. Why? Because you have no context about what x is. So you can't determine if it's a true or false statement. So that's not a proposition, okay? C is the statement 1 is greater than 2. That's a proposition, okay? Even though it's false, that's fine. Propositions can be true or false. And D is the statement 10 minus 2 is 8. That's a proposition, and that's true. Okay, so the answer for number 1 was B, the statement x is less than 7. Okay, so anytime you were given a statement like this with a variable, and I'm not telling you what the variable is, or I don't give you a domain for the variable, that is not a proposition. Okay, so that was question 1. Okay, as we go through these, if you have any questions at any point, you can feel free to ask. All right. Question 2. Which of the following is a proposition? So the second question was which of the following is a proposition? Okay, and again, you were given 4 choices. A was a question, what's your name? Okay, questions are not propositions. They're not declarative statements. They don't have a truth value. B was a command, was go away. Okay, go away is a command. Commands are not propositions. Okay, again, they don't have a truth value. C, again, was not a proposition. C was the statement x plus y equals z. And D was a square has 3 sides. A square, so D, a square has 3 sides. Okay, again, that's a proposition, that's a declarative statement. So the answer for that was D. All right, let me try. Okay, let's move on to the next question, 3. 3 asked which of the following is true. Okay, so these are all of the following 4 choices were true. Were propositions, and you had to determine which one was true. Okay, so 3, which is true? Which is true? All right, so your first choice was the statement if 2 plus 2 equals 4, then 1 plus 1 equals 3. Okay, so the way to do this was you just had to go by the rules for the different compound propositions when they're true and when they're false. All right, so if you have a conditional statement, remember a conditional statement is always true, except in one case. It's only going to be false when the hypothesis is true, but the conclusion is false. Okay. And for biconditional statements will only be true when both the parts have the same truth value. So whether they're both true or both false. Okay. All right. So your first choice here was if 2 plus 2 equals 4, then 1 plus 1 equals 3. So for that, 2 plus 2 equals 4, that's true. 1 plus 1 equals 3, that's false. So since this is a conditional statement, the hypothesis is true, the conclusion is false, the statement will be false. So A is false. Okay. B, If 2 plus 2 equals 5, then dogs can fly. 2 plus 2 does not equal 5. Dogs cannot fly, so that's false and false. So a conditional statement where the hypothesis and the conclusion are both false is true. So B is the true one. Okay, B. If 2 plus 2 equals 5, then dogs can fly. Okay. For part C and part D, those were biconditional. For answers C and D, those were biconditional statements where the two parts had different truth values. So they were both false. Okay, right? So the C was 2 plus 2 equals 5 if and only if 1 plus 1 equals 2. Right? The first is false, the second is true, different truth values. And D was 2 plus 2 equals 4 if and only if dogs can fly. So one is true, one is false. Again, two different truth values, so that would be false. Okay, so the true one was D. All right, moving on to number 4. Okay, 4 was the question. Which of the following is the inverse of the proposition? If the fruit is ripe, then I will eat it. Okay, if the fruit is ripe, then I will eat it. So what is the inverse? We're looking for the inverse. Okay, so the inverse means we negate both the hypothesis and the conclusion. So the inverse would be the sentence, if the fruit is not ripe, then I will not eat it. Okay, that would be the inverse. So the choices were A, if the fruit is not ripe, then I will not eat it. So that means 4 is A. Okay, that's the correct one. B was it is not the case that the fruit it is not the case that if the fruit is ripe, then I will eat it. Okay, that is the negation of the entire sentence, not the negation of each of the parts. Okay, so B is not correct. C, if I will eat it, then the fruit is ripe. That is the converse, not the inverse. And D is, if I will not eat it, then the fruit is not ripe. That's the contrapositive. Okay, so the answer for 4 was A. Okay, let's move on to 5. 5 was the question, which of the following is logically equivalent to the proposition, if the fruit is ripe, then I will eat it? So that would be the contrapositive. You had to remember that a conditional statement is logically equivalent to its contrapositive. So the contrapositive is both the inverse and the converse. So that would be D in this question, right? If I will not eat it, then the fruit is not ripe. Okay. Which is logically equivalent, right? So that's the contrapositive. Okay, which was D. All right, if I will not eat it, then the fruit is not ripe. Okay. Let's move on to question 6. 6, which of the following is a tautology? Okay, so we were given 4 here. If you weren't sure which was or was not a tautology, you could do a truth table. Remember, what's a tautology? A tautology is a compound proposition that is always true no matter the values of the propositional variables. Okay, so something that's always true. So A was P or not P. Okay. B was P and not P. C was it is not the case that if P then Q. D was P and not Q. Okay, so for of these 4, A is the one that's a tautology, P or not P. Okay, That one is always true, right? Because either P will be true, or if P is false, then not P will be true. So one of the two will always be true. So the disjunction will always be true. And you could have done that with a truth table. I think we even did a truth table for this in class. Right? P is either true or false. Not P will be false, true, the opposite truth value. So the disjunction P or not P will be true, true. Okay, so it's always true. It's a tautology. Okay. 7 asked which of the following is a contradiction. Okay, remember contradiction is a proposition, a compound proposition that's always false. Okay, so this one you have the same 4 choices. The answer was B. All right, P and not P. And again, if you weren't sure why, you could have done a truth table, right? P and not P will have truth values. So they can't both be true at the same time. So this conjunction will always have to be false, right? Let's see the truth table. P, we don't know what it is. It's either true or false. Not P will have opposite truth values. And a conjunction can only be true when both parts are true. So this will always be false. It's a contradiction. Okay. Question 8. So 8, 9, and 10 dealt with quantifiers. 8 said, which of the following is true if the domain consists of all real numbers? So which is true for I believe for all of these questions, the domain was the set of real numbers, right? So which is true? All right, so we were given 4 options. Let's go through them. A was the quantified statement. There exists a real number x such that x is greater than x plus 1. Okay, that's false, right? You take any real number and add 1 to it, the result will be bigger, not smaller. Okay, so this is a false statement. B was the statement there exists a real number x such that x squared equals -1. Okay, that's also false, because what would x have to be? X would have to be the square root of -1, which is not a real number. So there is no real number x such that x squared equals -1. Okay, no real number squared will be a negative number. All right, so our search continues. Part C. C was the statement for all x, -x squared equals x squared. For all real numbers x, -x squared equals x squared. Okay, that's true, right? Take any negative number and square it. That's the same thing as that number x squared. Okay, so that's true. So that's the true one. D, we'll go over D as well. D is also false. D was the statement for all x squared is not equal to x. For all real numbers x squared is not equal to x. That's false, right? Because if x equals false. If x equals 0, 0 equals 0 squared, so x will equal to x squared. And same thing with 1, right? If x equals 1, 1 equals 1 squared. So x will equal x squared. Okay, so the true one is C. So C was the answer. All right, moving on to 9. 9 asked which of the following is true, again, if the domain consists of all real numbers, and this one had nested quantifiers. So which of the following is true? Okay, let's go through all 4 of them again. And again, the domain is all real numbers. So the first one was there exists an x such that for all y, if y is not equal to 0, x times y equals 1. Okay. All right. So is that true or is that false. There exists some real number x such that for all real numbers y, as long as y is not equal to 0, x times y equals 1. Okay, that's false, right? Because that's saying that there exists one real number, there exists some real number x that no matter what I multiply it by, as long as I'm not multiplying it by 0, the product will always be 1. Okay, that's not true. There is no such number, that no matter what I multiply it by, the result will be 1. Okay, so that's false. So our search continues. Let's move on to part B. Okay, B was the statement for all x. If x is not equal to 0, then there exists a y such that x times y equals 1. Okay. That one is true. All right, this is saying for all real numbers x, as long as x does not equal to 0, there exists some number y that we can multiply x by to get 1. Right? What number is that? It's reciprocal. Okay, so this is the idea that every real number besides 0 has a multiplicative inverse. Okay, that's true. Okay, so the answer here was B. Let's just go through the others to see why they were false. C was the statement, there exists an x, there exists a y, such that x plus y does not equal y plus x. Okay, that's false, right? For real numbers, all real numbers have the commutative property. So for all real numbers, x plus y will equal y plus x, that's false. And D was the statement, for all x, there exists a y, such that x equals y squared. Such that x equals y squared. Okay, so for all real numbers x, there exists a y such that x equals y squared. That's also false. Why is that false? Well, let's say x is -1. Right, similar to what we had before. If x is -1, there is no real number y such that y squared would be -1, right? Y would have to be the square root of -1, which is not real. So it's not in the domain. Okay, so that's a false statement. So the answer for this was B. Okay, any questions on number 9? Okay, let's move on to number 10. 10 asked, which of the following is false if the domain consists of all real numbers? Okay, so which is false? Okay. So A was the statement for all x. X squared plus 2 is greater than or equal to 1. Okay, that's true, right? The smallest x squared could be is 0. 0 plus 2 would be 2. So x squared plus 2 will always be greater than or equal to 1, right? The smallest it could be is 2. So that's true. Okay, we're looking for the false one, so we continue. B was the statement, there exists an x such that x to the 4th is less than x squared. Okay, that's true as well, right? Let's say x equals 1/2. Okay, 1/2 squared is greater than 1/4 squared. Okay, so that's true. Our search continues. C is the statement for all x, x is less than x plus 1. Yeah, we discussed this one before. This is the reversion that's true, right? Take any real number x, add 1, you'll get something that's bigger, so that's true. So we're left with part D. D is going to have to be the false one. What was D? D was the statement, there exists an x such that x squared equals -2. So there exists some real number x such that x squared equals -2. And again, that's false for the same reason we mentioned above. x would have to be the square root of -2, which is not real. Okay, so there is no real number. There's no number in the domain that will make x squared equal to the negative number. Okay, so we found our answer for 10. The answer is D. Okay. Any questions on that? Okay. How many points is the multiple choice section? So the multiple choice was worth a total of 40 points, and the other questions were worth a total of 60 points. Okay. All right. There is a little bit of a curve, which I will discuss soon. Okay. All right. Well, we'll discuss that at the end. All right. 7. 7 was B. Okay. All right. Let's continue with the rest of the questions now. Okay. 11 is as follows. 11 asked you, use a truth table to determine if the proposition, the negation of P if and only if Q, is logically equivalent to if P and Q, then not Q or P, and determine whether each of these propositions is a tautology, a contradiction, or a contingency. Okay. Okay. So we're looking at these two propositions here. The negation of P if and only if Q. We want to see, is that logically equivalent to if P and Q, then not Q or P. Okay, and we also want to see if any of these are a tautology or contradiction or contingency. Okay, so let's do a truth table. We have P, we have Q. All right, we have a not Q here. There's no not P, so I'm not going to bother with that. We have P if and only if Q, and then we have its negation, the negation of P if and only if Q. All right, and then we have P and Q, not Q or P, and then the conditional statement, if P and Q, then not Q or P. Okay, so those are all the columns that you need in your truth table. Let's start filling it in. So P, 4 possibilities, true, true, false, false. For Q, true, false, true, false. Okay. That gives us our 4 possible cases. Not Q will be the opposite truth values of Q. So false, true, true. Okay. P if and only if Q will be true whenever P and Q have the same truth values. So it's going to be true, false, false, true. The negation of P if and only if Q will have the opposite truth values of P if and only if Q. So wherever P if and only if Q is true, its negation will be false and vice versa. So false, true, true, false. Okay. So that's the first proposition here. The negation of P if and only if Q, those are its truth values. We see right away that that one is not a contradiction, nor is it a tautology. It has to be a contingency, right? So this one is a contingency, right? Because it can sometimes be true, sometimes be false. That means it's a contingency. Let's do the next one now. P and Q, it's true when both parts are true. So true, false, false, false. Not Q or P is true as long as one of them is true. So true, 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 false, true. Okay. And finally, the conditional statement will be true as long as the hypothesis, when the hypothesis is true, the conclusion is true. So true, 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 false, true, true, false, false, true, false, true, true. So we see right away that this proposition is a tautology. It's always true. Okay, so one is a contingency, one is a tautology, but the two are not logically equivalent. Okay, so they are not logically equivalent. They have different truth values. Okay. All right, any questions on number 11? Okay, let's move on to number 12. Okay, question 12 asked, express each of these statements using predicates, quantifiers, logical connectives, and mathematical operators where the domain consists of all integers. So the domain is the set of integers, okay? Okay. You were given 3 questions, 12, A, B, and C. A was the sentence, the average of 2 positive integers is positive. Okay. All right, so here in this sentence, we're dealing with 2 positive integers. So the domain was the set of integers. We want to talk about positive integers. Okay, so we're going to have to restrict our domain. Okay, so we have 2 variables, 2 integers, 2 variables. So we'll write it as for all x, for all y, for all integers x, for all integers y. Okay, now this is existential. We're talking about all positive integers. So when we restrict a domain with existential quantifiers, we have to write it as a conditional statement. So we're going to say, for all integers x and y, if x is greater than 0, it's positive, and y is greater than 0, it's positive, then their average is positive. So if x is greater than 0 and y is greater than 0, then their average, how do I write their average? X plus y over 2 is greater than 0. Okay, so that would be the answer for part A. There were a couple of different ways people did it. If you did it in a slightly different way, as long as it was still accurate, you got it right. Okay. Oh, somebody asked, is number 11 logical equivalent? Yeah, they are not logically equivalent in number 11. Okay. So they were not. In number 11, they were not logically equivalent. All right. All right, let's move on to part B. Okay, part B was the statement, the product of 2 negative integers is positive. Okay, so again, we need to restrict our domain. We're talking about all integers. Okay, so it's existential, where there's 2 of them, so we need 2 variables. And we want to restrict our domain to the negative integers. So we'll say for all integers x, for all integers y. If x and y are negative, they're less than 0. So if x is less than 0 and y is less than 0, then their product will be positive. So x times y will be greater than 0. Okay, so that's how we would do that. And again, there might have been a couple of different ways you could have done it. As long as your answer was correct, I would give you credit for it. Okay. You forgot to put the plus sign. Which plus sign are you referring to? 12a. You mean to make it positive integers? Yeah. If you forgot that, if you did not restrict the domain. Oh, you mean for the average? You're talking about the average. Yeah. Depending on how you did it, then yeah, you could have lost points for that, a few points, like maybe one or 2 points, not that much. Parentheses, no. I would if it's clear to me what you wrote, even without parentheses, then I wouldn't take off points for that. I just put the parentheses to make sure it's clear what I intend. Okay. So no problem. Okay. let's do part C. C was the statement. The difference of two negative integers is not necessarily negative. The difference of two negative integers is not necessarily negative. Right? Could be positive, could be negative. Okay. So there were a couple of different ways you could have done this one also, because a lot of you did it in a few different ways. For this one, I'm going to do it one particular way here, but if you did it in a different way, as long as your answer was correct, you got it right. All right. So for this one, again, we're talking about two integers. We're talking about two negative integers. Okay. So I'm going to have to restrict the domain. I'm going to have two variables and restrict the domain to the negative integers. And if I want to say that their difference is not necessarily negative, then I'm saying that there exists some pair of negative integers whose difference is positive, right? That's one way of putting it. So that's how I'm going to put it, okay? So there exists an x, there exists y, there exists integers x and y, such that x and y are negative, x is less than 0 and y is less than 0. Okay, and since this is existentially quantified, I'm going to write this as a conjunction, not as a conditional statement. And x minus y will be positive. Well, I say positive, but actually, if it's not necessarily negative, then it could be positive or 0, so greater than or equal to 0. Okay, so this is one way of doing it. You could have also done this with universal quantifiers, and there was a couple of different ways you could have done it. Any of those ways would have been fine. Okay. All right, any questions on that? Okay, so yeah, so not necessarily negative means that it's positive or 0 as well. It could be positive, it could be 0. Depends. If you used universal quantifiers, then you should have used a conditional statement. If you use existential quantifiers, then you should have used conjunction. Okay. Yeah, so that would have been fine too. Okay, if you use universal quantifiers, you could have written it that way, where you write the x is less than 0 and y is less than 0. Then it could be greater than or equal to 0 or less than or equal to 0. That was fine. If you were using existential quantifiers, then you really should have used a conjunction as opposed to a conditional statement. Okay. Yeah, you would have lost some points on it. It also depends on how you wrote it, but yeah, you would have lost a little bit on that. Not that much, but a little bit. Okay. Oh, that goes back into again to our whole discussion about restricting domain with the different quantifiers. All right, so you'd have to go back to that. Okay, the basic idea was whenever you had a universal quantifier and you want to restrict your domain, you should use a conditional statement. If it's an existential quantifier, you should use a conjunction, okay? The negation of x minus y less than 0 would be correct. Yeah, that would be fine too. All right. Okay. All right, let's move on to 13 now. All right, 13 was as follows. Translate each of these expressions into an English statement. The domain for all variables consists of all real numbers. I asked you to write your final answer as a sentence without variables. Okay, so 13a, write the sentence in English. You were given the sentence. There exists an x, there exists a y, such that x is less than or equal to 0, and y is less than or equal to 0, and x minus y is greater than 0. Okay. Okay, so this statement is actually very similar to the one just before. Okay. Again, there were a couple of ways you could have written it. So I would write it as follows. One possible option would be to write it this way. There exist two. So if x and y are less than or equal to 0, then they are non-positive. Right? That's one way of saying it. So you could have either written less than or equal to 0, or you could write non-positive. So there exist two non-positive real numbers whose difference, right, x minus y, that's their difference, whose difference is positive. Right? Greater than 0 means positive. Okay. And there were a bunch of different ways you could have said it that were equivalent to saying this. Any of those ways would have been marked correctly. Okay. Let's move on to B. B was the statement for all x, for all y, x is greater than or equal to 0 and y is less than 0 implies x minus y is greater than 0. Okay. So for all x, for all y, x greater than or equal to 0 and y less than 0 implies that x minus y is greater than 0. Okay. All right, so for all real numbers x and y, if x is non-negative and y is negative, their difference will be positive. So in other words, the difference of a non-negative, right, greater than or equal to 0 is another way of saying that is to say non-negative. So the difference of a non-negative real number and a negative real number is positive. Right? It's greater than 0. Okay, that was 13. I forgot to write positive after none. I wrote two non-real. I'd have to go back and check how I graded it, but if I understood what you meant, then I would have graded it correctly. Okay. Okay, let's move on to 14. So now we get to the proofs. 14, prove that if x cubed is irrational, then x is irrational. And I asked you to tell me what type of proof you used. So if x cubed is irrational, then x is irrational. Okay, so here, this is a conditional statement. And remember, I told you that in general, if the hypothesis has an expression that's more complicated than the conclusion, try an indirect proof, right? So here, x cubed is an expression a little bit more complex than x. So let's try an indirect proof here. What I'm going to do is I'm going to use a proof by contraposition. If you did a proof by contradiction, that works as well. So either one would have been fine. So, but for here, let's do this by proof by contraposition. Okay. So the contrapositive would be the statement if x is rational, then x cubed is rational. If x is rational, then x cubed is rational. Okay, we're going to prove this statement by direct proof. So if we assume x is rational, then an x equals p over q, where p and q are integers, and q is not equal to 0. I'm not going to write the whole thing out, but right, that you should write that out. So x equals p over q, p and q are integers, q is not 0. If I cube this now, p over q cubed will be p cubed over q cubed. P cubed and q cubed are both integers. Okay, and the denominator is not 0 because q is not 0. So by definition, x cubed is rational. So the proof is done. We showed when x is rational, x cubed is rational. So if x cubed is irrational, x will be irrational as well. Okay. Questions on 14. Can you show, I'm not sure that we're going to have time for me to show that. Maybe at a later time, if you like, I can show you that. It's very similar. It's a very similar idea. Right? You just, you have to prove that the negation is true. So the negation would be the statement, what, P and not Q. So x cubed is irrational and x is rational. So you show that that leads to a contradiction, right? Well, if x is rational, then x cubed has to be rational, and that contradicts the statement that x cubed is irrational, right? That would be the idea. Okay, let's move on to 15. Okay, 15 was the one that I changed. Some people, they did the problem that was on the test and not the correction. Either way you did it was fine. I graded it either way. The reason I changed it is because I wanted to give you a shorter problem that would be faster to do, that wouldn't take as much time. So the one I asked you to prove was prove that prove the statement n squared is odd if and only if 1 minus n is even. Right? N squared is odd if and only if 1 minus n is even. So that's what I asked you to prove. So this is a biconditional statement. So you have to prove it both ways. We have to prove that when n squared is odd, 1 minus n is even. And when 1 minus n is even, n squared will be odd. Okay, so let's start with that. N squared, if n squared is odd, then 1 minus n is even. Let's start with that. Okay, and then we'll prove it the other way. Okay, so we know if n squared is odd, then we know we discussed in class, and you could have proved it as well in the test. You didn't really have to, though. If n squared is odd, n has to be odd, right? So if n is odd, that means n equals to 2k plus 1 for some integer k. So what will 1 minus n be equal to? 1 minus n will be 1 minus 2k plus 1, which equals to negative 2k. Right? 1 minus 1 will be 0. That will cancel. So we're left with negative 2k. Negative 2k is equal to 2 times negative k. So by definition, that's 2 times an integer. That's even. Okay. So if n squared is odd, 1 minus n will be even. So we proved it the first way by direct proof. Now let's go the other way. We have to prove if 1 minus n is even, then n squared is odd. Okay. So direct proof, we assume 1 minus n is even. That means it equals to 2k for some integer k. All right, let's solve for n. If I solve for n, I get n equals to negative 2k plus 1. All right, now let's get n squared. So we'll square both sides. Squared, squared. I get n squared will equal to, if you square that, you're going to get 4k squared minus 4k plus 1. Okay, and that's odd. How do I know that's odd? I can factor out a 2 from the first two terms. I get 2 times 2k squared minus 2k plus 1. So I have 2 times an integer plus 1. That's odd. Okay, so if 1 minus n is even, it's even, then n squared has to be odd. And the proof is done. So as long as you proved it both ways, you were good. Okay. For this one, I believe it was n squared. Yeah. If you did the original problem, then part C was n cubed is odd. That was in there as well. Okay, so if you did that, okay, yeah. All right, so I'm not going to go over that entire one now. If you want to see that, I can do it later at a later date as well. But yeah. Okay. Okay. All right. Let's now move on to 16. All right. So for 16, so this is the curve I was talking about earlier. 16, enough people had trouble with 16 that I decided to eliminate that question. So I just gave everybody credit for 16. Okay. 16 was as follows. It said prove that there is a rational number x and an irrational number y, such that x to the y is irrational. And then I asked you, is it constructive or non-constructive, your proof? Yeah, the quiz. We're gonna finish up with this problem, and then I will send you off to do your quiz. Okay. All right. All right. Review. I don't think we're gonna have so much time for a review. Maybe we'll do a quick one. All right. Okay. One moment. Okay. All right. Was there extra credit for that? No, there was no extra credit for that one. Okay. I basically just I decided to, yeah, for 16. Yeah, that's what I'm talking about also. Okay. Okay. So how do we show that this is true? So let's say we pick x equals 2 and y equals to the square root of 2. Okay. So x to the y would be 2 to the power of the square root of 2. So x is rational, y is irrational. Now 2 to the power of the square root of 2, I don't know what that is. If it's irrational, then we're done. We found an answer. If it's irrational, we're done. Okay. If it's rational, then do the following. Let x equals to 2 to the square root of 2. That's rational. Let y equal to the square root of 2 over 4, which would be irrational, okay, because the square root of 2 is irrational. Then x to the y would be 2 to the square root of 2 to the square root of 2 over 4. Square root of 2 times square root of 2 would be 2, so this would be 2 to the 2 over 4, which is 2 to the half, which is the square root of 2, which is irrational. So I would have an irrational number raised, I would have a rational number raised to an irrational number that is irrational. Okay, so this is a non-constructive proof, and that's how it would look. Okay, so that's the end of the exam. Okay. Yes. Okay. Let's see. Okay. For this one, if you wanted, if constructive, could we have just have the if irrational part? Well, I would have to see what you did, to be honest, in the proof. Okay. Yeah, I would have to see what you did. Okay. All right. The quiz will start at 6 o'clock, so you've got a couple of minutes. There are 10 questions. They're all true or false questions, okay? All right. So if you want, you can start logging on to Blackboard. That should be available in a minute, okay? In the next 2 or 3 minutes, let me just do a quick review of what we did last time. Okay, if anyone does anyone have any questions before? Or you'll have 15 minutes to do it. All right, so at 6:15, it will end. Yeah, it will only cover 2.1 and 2.2, which was our original plan. Okay, so nothing about functions. U and N, I assume you mean for the union and intersection? The unions in general is not really that hard unless you're talking about union of a collection of sets. Yeah, a union of a generalized union or a generalized intersection. That sometimes is a little challenging. Okay. But if you go over the problems we did in class and some of the homework questions, then you sort of kind of get a feel for it. All of the problems would look similar to those, more or less. Okay, some variation of those. Okay. All right. Any other questions? Subset and proper subset. Yeah. All right. So if the quiz is going to be on Blackboard, so I suggest everyone now. You got 2 minutes. I say everyone now log on to Blackboard since the quiz will be available in a couple of minutes. Okay. Blackboard. If you look on the left, there'll be a option that says quizzes on the left. So you click on that, then you'll see it in another minute or two. All right. Subsets and proper subsets. Okay. One set is a subset of another set. If all of the elements in that set also appear in the other set, okay? So if I say something is this, if I say A is a subset of B, that means that either A is smaller than B, or it can also be equal to B, all right? So subset means subset or equal. If I talk about a proper subset, then that means that if A is a proper subset of B, then A has to be smaller than B. It can't be equal to B. Okay, so if A is a subset of B, it can be equal to B or have less elements than B. If A is a proper subset of B, it has to have less elements than B. It cannot be equal to B. All right. Yeah, you can think of it that way. Okay, and remember it has to have all the elements, right?
Quick question.
Yes.
If A is a subset of B, then B is a proper subset of A?
No. If A is a subset of B, B could possibly be a subset of A, or not. It depends if they're equal. If they're equal, then A is a subset of B and B is a subset of A. Okay. If they're not equal, then A is a proper subset of B, but B would not be a proper subset of A. Okay. All right, B is larger, so it can't be a subset of A. Okay. To be an element, it would have to, it's 6 o'clock, so you guys should be able to see the quiz now. You can start. I'll just answer this final question here. What is the empty set? Why is the empty set a subset of all sets, but not an element of all sets? Well, to be an element, it would have to actually be, you'd have to actually see it there in the set. All right. Don't see it yet? All right, give me a minute here. Give me a minute. Let me take a look here. Oh, give me 1 second. Okay, check again. You should see it now. All right, refresh your page. Yeah, and you should see it. Okay. Okay, good luck, everybody. I'm here. I'm going to stop recording at this point.